In numerical analysis, a bisection method is a tool that helps us to find out an approximate real root of a given function. The Bolzano's theorem forms the basic building block for bisection method. Bolzano's theorem tells us that if we can somehow find two distinct points on the horizontal axis, corresponding to which the function takes values of opposite signs, one positive and the other negative, then a root of the given function must lie between those two distinct points. Finding out these two distinct points is the first step involved in bisection method. Let's take an example to explain what this method is all about.
Let's say we wish to find out an approximate root of this function. At the point 0, the function takes a positive value, while at the point 1, the function takes a negative value. If we zoom in this picture, this is what we're looking at. So by Bolzano's theorem, a root of the given function lies between 0 and 1. In other words, a root of the given function lies in this interval.
Okay, but why did we choose 0 and 1? We could have chosen, say, 2 and 100 as well. If we take x equal to 2, the function takes a negative value. If we take x equal to 100, the function takes a positive value. So Bolzano's theorem is applicable here as well. So why did we choose 0 and 1 instead of choosing something like 2 and 100? We'll get back to that in a moment.
Let's now take the midpoint of this interval. Corresponding to this midpoint, the function takes a negative value. This can also be shown mathematically. So by Bolzano's theorem, the root of this function lies between 0 and 0.5. So while we started off claiming that a root of the function lies in this interval, we now find that this interval reduces to this. If we zoom in this picture, this is what we are looking at. Let's again take the midpoint of this interval. Corresponding to this midpoint, the function takes a negative value, which can again be shown mathematically. So by Bolzano's theorem, the root of this function lies between 0 and 0.25. So while our previous claim was that the root of the function lies in this interval, we now find that this interval reduces to this. If we zoom in this picture, this is what we are looking at. Let's again take the midpoint of this interval. Corresponding to this midpoint, the function takes a negative value, which can again be shown mathematically. So by Bolzano's theorem, the root of this function lies between 0 and 0.125. Our previous claim was that the root of the function lies in this interval. But we now find that this interval reduces to this. Let's zoom in this picture. This is what we are looking at. If we take the midpoint of this interval, we find that the function takes a positive value. So by Bolzano's theorem, a root of this function lies between these two distinct points. So our previous interval gets reduced even further.
Alright, so basically we start off by claiming that a root of the given function lies in this interval. We take the midpoint of this interval, so we kind of bisect this interval into two different parts, and then we remove one of its parts. And then we do the same with the remaining interval. We take its midpoint, bisect it, and then remove one of its parts. And we just keep doing that. We keep bisecting and compressing our intervals till we reach a point where our intervals become so small that it almost coincides with the root of the function. This is how a bisection method works. But this is a rather abstract way of looking at it. Mathematically, we need something much more concrete. At what point do you stop bisecting your intervals? At what point do you stop and say, alright, this is the root that I'm looking for? Well, that actually depends on what you're trying to find out. If we go back to our example,
let's say we wish to find out the approximate root of the given function correct to 2 decimal places. So we find out all these midpoints. Now out of all these midpoints, this is the first pair of consecutive midpoints in which the digits before the decimal point and the first 2 digits after the decimal point are exactly the same. And why are we considering only the first 2 digits after the decimal point? Well, that's because we want to find out the root to 2 decimal places. And well, we stop here and we say that this is the root of the given function.
Now coming back to our previous question on why we had chosen 0 and 1 and not 2 and 100. Well, the truth is there's nothing wrong with choosing 2 and 100 as well. It's just that the interval 2 to 100 is much larger as compared to the interval 0 to 1. When you choose a smaller interval, you're actually already pretty close to the root of the function. So you just need to slightly squeeze your interval to get to the actual root. So this means you don't really need to apply bisection method too many times. This saves a lot of time and calculation. But if you choose a larger interval, you need to squeeze and compress your interval quite substantially, and that involves lots of steps, calculation and time. So if you wish to save time, just take a small interval.